Hello and welcome to this video which introduces Python scripting in OPTUM GX. Just some basic concepts to get started. What is Python? Well, Python is, as it says here, a widely used, easy to read programming language for data processing and scientific computing, and actually a lot of other things as well. It's a high-level language like MATLAB, and it has one of the advantages of Python. First of all, it's free. And secondly, it has a huge number of modules for doing all kinds of specialized things attached to it. So I have not come across anything that I could not find a module to do. So it's a very powerful language, and it is widely used, and I think its use is actually increasing. And a script, well, a script is then a collection of commands, you could say, or a sequence of instructions that are executed automatically. So a script is a sort of a small mini program that does something. And in GX, the idea is that Python is used as the scripting language to create and modify models, run analysis, and extract and process results after the analysis has been completed. In practice, it works by working with Python as you normally would, except if you import a special GX module, then that allows you to communicate directly with the GX user interface. Of course, all the other Python functionality is still available. So we talk about a kind of a remote control of the user interface with all the instructions, with all the commands that make up your script, of course, being saved in a text file so you can modify them and execute them whenever you're ready to basically do the same kind of things that you would otherwise do manually with mouse clicks. So it's something that's very powerful for automation, for parametric studies, and in many other ways as well. So just the bare essentials of Python scripting in GX. So as I said, for every function in the user interface, there is an equivalent Python command. For example, if you want to draw a line, well, in the user interface, you select the line tool, pick the first point and the second point. There is an equivalent Python command which is called add line, which takes two arguments, the first point and the second point. Running an analysis, there's the play button in the user interface. In Python scripting, it is a command called run analysis. Then I just have to touch, I don't want to go into it in a great amount of detail, but just to say that this scripting language is object-oriented, so there's a hierarchy of objects. They're shown here. So the top level is what we call the application, which is the program itself, which has functions, or object-oriented language, you would call them methods, for doing various things, for loading and saving files, and also for creating a new project. Once you have the project, that's the next level, then there's methods attached to that. For example, run analysis, that's pressing the play button, that's a project level command in the UI, and it's the same in Python. Creating a new model, that's also a project function. The next level is the model level, which is where you tend to spend most of your time. That's where you define geometry, load, supports, etc. And you can also create a new stage, which brings us to the fourth level, which is the stage level, where there's functionality, there's methods for toggling features, for switching things on and off, for setting the analysis type, and also in setting the from stage and various other things. And then finally, there's a kind of an output object that are attached to a model, if you only have a single model, or else if you have a model with stages, then it's attached to each stage. So the model object basically contains all the results of the analysis. Everything you can visualize in the UI under results is available there as numbers. So a very simple example. So this uppercase GX is what we call the class. And this lowercase GX, we here create an object So that's the top level application object. And this object has a number of methods attached to it. And one of those is called create new project. So we create a new project. We call this object PRJ. And then this project object also has methods, for example, create new model. So we create a new model, we call it MOD, and that model has various properties, for example, the name, so mod.name is called new model, and a mod.addLine, it's more of a sort of an action. It's a method where we create a new line from 0,0 to 2.4. And a very important point that I'll illustrate shortly is that as you work with the UI in GX, you are actually recording or generating automatically behind the scenes a script that you can then later access. That's an extremely useful functionality, both in terms of learning the scripting language and also in terms of, say, minimizing the amount of coding you have to do. A lot of the time you can play around a little bit with the mouse and then record a script, take that script and modify it appropriately. We'll do that in a second. So that's a very powerful functionality. Something else that's, I think, very convenient is the GX ships with Python, with a Python interpreter. That's Python 3.11, so it's not the very newest one, but I think it's okay. And then Spider 6.0 for basically setting up and debugging and executing your scripts. So there's no need to download anything. Everything is available when you have installed GX to really get going. If you want to use an alternative Python IDE, I know a lot of people like VS Code, then that's entirely possible as well. There are details. You'll have to sort of set it up yourself, but it's relatively easy. And there are detailed instructions on our webpage on how to do that. Or if you want a newer version of Spider, I think this is very new as of August 2026, but there will probably be newer releases. And if you want to use one of those, or indeed, if you already have Spider installed and you don't want another version of Spider, then you can, it's not going to interfere with the version you already have. But if you want to use your own private version, then you can find instructions here on how to set that up. But in the first instance, no need to download or set anything up. Everything works out of the box. And now I'll switch to GX. And as I said, when you work with the UI here, a Python script is automatically generated behind the scenes. And to illustrate that, I will go with my sort of default example of it's a foundation, limit analysis of a foundation, or load multiplier analysis of a foundation. So I draw the soil domain here. And if I go up here and then select Python, project Python code, well, then you can see some code has been generated. Let me just make that a little bit larger. So here is a, to start with, just a comment. Then this is the OPTUM GX module that you import that allows you to basically communicate with the user interface. We create this top-level application object, GX, and then we create a project. So that's gx.createProject, and we have, it's called, the default name here is untitled project. And then we create a model, that's the default model, model A. So okay, we get the model, but the model is already there. So we don't actually create a new model in this case. And then we take the model and we add a rectangle. And that's from 0,0 down here to 10,5 up here. Then let's draw a foundation. Like that. And that's another rectangle from 0,5 to 2,6 from here to here. Then let's apply some material. Let's take the NC basic. And what is done here is that it's actually three commands that are generated here. First of all, we select. I cheated a little bit because I dragged and dropped, but typically we would select a face, and then we get the material here, and then we apply that material to the selected shape. Let's try to do it with the foundation instead. So I select, and then I apply. I get my rigid material and I apply it. So I've selected. So model.select, and that's a point at the center of the face. The type of object I'm selecting here is a face, and I get the material. The material lives at the project level, and then I apply that material to the selected shape. Next is loads, and I need a multiplier surface load like that. And you can see I again select the shape. That's an edge now, and then I apply a load. So I say model dot set surface load to that shape that I've just selected. A value of -1, direction is the Y, and option multiplier. If I wanted to change this to say, instead of having a unit load, let's have a load of 10. Well, then I have my load object here. So I say load.p equal to -10. Good. Standard fixities. You tend to do it like that, and that's just simply model.set standard fixities. Then I need to go over to load multiplier analysis, and that's a model property, analysis type, load multiplier, and I am basically ready to go. You can see I run the analysis here. And that's it. So this is my script that has been generated automatically. If I want to continue working with this script, what I can do is I need my Python IDE. IDE stands for Integrated Development Environment, and that's where Spider comes in. So I open up Spider. Just be aware the first time you open up Spider, the first time you click this button, it takes quite a while because a so-called virtual environment has to be generated, and that does take quite a while. And then on subsequent openings of it's much faster. So we already actually have a default script, but let's just have something completely blank. So this is how it looks. On the left here, we have basically a text editor, and on the right, we have the Python command window where we can write 1 + 1 = 2, and we can write any command basically. Possibly when you open it up, it's going to look something like this. There's going to be all kinds of windows up here that you can then just close or keep them open if whatever you want. I like to close them. We can then take our script here, select all, copy it, and then let's just close that down. We don't need it anymore. And then paste it into the text editor here. And it's exactly the same as we had before. And then we can execute that. We can run that script. But before we do that, let's just take a new blank project. So we are sure that, maybe make this window a bit smaller. You can see that it actually happens. So just run the project, and then it starts up and runs, and we're done. We could have included We could have included here a model dot zoom all before we run the analysis, and then we'll just have sort of fitted the model to the window. What about results? Well, results are attached to the model. So we have this model object, and if I write model dot output, then all the results are here, and they are grouped into various sort of categories. There's one called critical result. That's sort of some key results, like the load multiplier. It's of course model dot output dot critical results. We have model dot output dot solid. That's the solid elements. There's 962 of them, and if you want the first one, then that's this one, and we have results. Then there's collapse mechanism, and UX, for example, and that both the units and the values are there. So those are the values at the corner of each triangle. That is also, I believe, something called topology, where you then have the X and Y coordinates of the triangles set here. I think it's just 0, yes. So that's the results you basically plot here, right? All of those results are available via Python. So that's how it works. And I thought it would be fun to do a bit of an exercise to sort of demonstrate a possible kind of use case of this kind of scripting language. I should say, of course, what I've done so far is I might as well have done it in the UI. Where this becomes powerful, of course, is if you parameterize this model. So, for example, we could have, say we wanted to determine the limit load for a range of friction angles. So the friction angle down here, if we just try to modify that, let's say 30, because then we get the equivalent Python command of how to do that. So we have already, I think we have already the material there, and then we say material.phi equal to 30. So what we could do in the script here is, after we basically get the material, we could say material phi, and let's call that phi. And then we could put a loop around all of this for I in range, let's say 25 to 35. And let's call this actually phi. Phi in range from 25 to 35 degrees. Do all of this and then set the material phi equal to this phi up here. And so there's going to be 25, then 26, etc. Run the analysis, and then what was it? The critical result, the collapse multiplier, that's this one here. So we could say load multiplier ln is equal to this, and then after each run we could print phi and the load multiplier. Let's see how that goes. So that's a bit strange. Oh, we keep applying the load here. Yeah, you have to be careful. and understand why does the load multiplier decrease with increasing friction angle, but we are actually applying the load multiplier, a new load of -10 at each time we run through the loop. So the safe thing to do is just to create a new project every time. It's very fast to set up, so you can sometimes save a little bit by not creating a brand new project every time, but in this case it doesn't really matter. So I think we should have an increase in load multiplier now, yes. So this is of course much faster than doing 10 of these runs with 10 different materials you would need manually. Similarly, changes to the geometry, if you want to investigate how do things look for different foundation widths, then that's straightforward as well. Okay, but a more, let's say, I wouldn't say it's exactly very practical, but more practical case is this kind of cantilever retaining wall shown here, where I think an interesting exercise would be to set up a parametric model of this problem here. And by a parametric model, I mean a model where you input this H here, the Q, the surcharge, the depth of the wall, and also the soil and wall parameters. And again, because then you can reuse that. So instead of setting up every model with mouse click, you can just enter a handful of parameters and then run the script, and you have what you need. So it's definitely quicker. But to do that, the way I would do it is I would set up a model, record the script, and then basically modify the script. So I have written some distances here. Let's say this is 4H, this is 3H, etc. So let's try to use those, and let me, while doing that, I would like to see both on the same screen like this. So I'm going to take the line tool, and then I'm going to make this, give this a length of 4, and this will be 3. This will be 2 and 1, and back here like that. Then I should be able to quickly modify that script, and let's have this one here. That's the D. Apply material. And let's modify the parameters. Let's say 0 and 30 degrees. And let's take a gamma of whatever, 16. Then let's try to apply a wall element. I'm just going to use a general plate, and the key quantity here is the yield moment. Modify that to 500 for the time being. And then also we have the interfaces here. So that's 0.67 and 0.67, 0.67. And then finally, standard fixities. And then a factor of safety analysis. So now I have sort of a base script that I can then take and modify. Select all, copy. and over to Python. Let's start a new project, and here are my lines then. So let me, let's say geometry. And then we have an h, let's say an h of 5 meters. Let's say a d of whatever, 4 meters. I think that's all I need. So this is where I added all those lines. So instead of 4 here, it should be 4 times h, 4 times h, 3 times h. It should actually, they should all actually just all be multiplied by h. Let me do that manually like that. It could be done more elegantly. And then model add line, that was for the wall. So it's at 2h comma 2h, point down here. And then down to the x coordinate is still 2 times h. And then the y coordinate is, what is the y coordinate here? It is h minus d. No, it is 2 times h minus d. Yes. So 3h is up here, minus h, that's 2h minus d. Let's see what this gives. That gives something, should be 4, that's correct, 5, and this should be 20 then. That's also correct. And then let's say soil. Let's say C, let's just say 0 cohesion, phi of, let's say 35, and gamma of 18. And then I go down to the material where I modified that manually. Let's say this is phi, and this is gamma. Oh, yeah, and let's see if that was understood. Yes, 0, 35, and 18. Then what oh yes, interesting, because the plate elements have disappeared now. And why have they disappeared? They've disappeared because the way I apply them in the script is I select an edge. For example, this one here. And the selection involves a coordinate, which of course is going to be different depending on my h and d here. So let's see what I did here. So I think I select this selection here. So I have 2 coordinates, and the first one I know is 2, the x coordinate is 2 times h, so that's kind of easy. And then we could say the middle point of this one up here, what is that? Well, what is the y coordinate? It's 3h up here, 2h here. So in between the center here, it's 2.5h. 2.5 times h. And the other one, well, this coordinate here is 2h. This one here is 2h minus d. So the mean value here is 2 times h plus 2 times h minus d divided by 2. Let's see if that applies the plate elements again. It does, so that's good. So that's part of the parametric model. And then I selected each of these. I believe I selected the first one up here first, and then modified the interface parameters. Not sure why that has already been, because my selection here really shouldn't be working. I think that's a bit of a coincidence. You have to select them properly and then apply the strength reduction factor. So the top one up here is 2 times h, and the coordinate here is 2.5 times h. And the bottom one, this is the coordinate, and then so just to test, I have 0.6 for the top and 0.5 at the bottom. 0.6 here and then 0.5 there, yes. So let's call this delta underscore phi. So delta on phi. And we have wall. And then let's use the standard 0.6667. And we also need a yield moment, plastic moment. Make that 800, and that's the one we set to 500 down there. So NP. Think we are pretty much set up now. Yes, that's 800. It's 2/3, and it's 2/3 there as well. And we have standard fixities and everything is running. So then we forgot the surcharge. No worries. How do we apply that? Well, you just apply it here. Oh, you just apply it here, and then let me just change the value so I know how to do that. And then I look at the Python project code. So shapes, select that shape. We again need a coordinate. We need to be a little bit careful with that, and let's introduce that here. So select, and what are the coordinates? What is the coordinate of the center here? It is 3h, 3h, as far as I can see. 3 times h times h. And let's call this, well, we can set it here. We can say Q, call it Q. Let's have a separate category here. Loads, and then Q is, let's take 20. And we are now set up. So that's pretty good. And all we need to do is basically say project run analysis, and then we can copy what we had from the other one. Yeah, why not copy both? And again, sort of maybe examine the effect of the friction angle on the whole thing. So we have a friction angle of, did we start at 35 degrees here? And no, it's not a load multiplier now, of course, it's a factor of safety, but that is also on the critical result, and it's called factor underscore of safety. Let's try. Yeah, then of course this LM is not defined. It's called FOS. But it seems to run. And we get 1.9 and it kind of looks believable. Sexual forces. The moment is well below the plastic moment. Try to set the plastic moment then to say 200. Then we should. Yes, then it's slightly below 1, and I think we should have the wall breaks like that. Yes. Well, you can very easily set up a model that so suppose we had the 35 here, and we're at this value here. Well, then we would have needed to give it some extra depth. Maybe that wouldn't even be enough actually. Let's see. I don't think so, because it's the wall that fails. Yes, that doesn't make any difference. But let's say it was 500, and there's obviously going to be an effect. As long as the wall doesn't yield, there's going to be an effect on the depth of the wall. So this is 4 meters depth. So 1.19, and if our target FOS was say 1, then we could try with 3. And that's actually very close to 1, so whatever, 3.1 or something like that. So these iterations to determine the necessary depth of the wall are also much easier to carry out if you already have a script. There's of course some work involved in getting the script up and running, but the advantage is you have a completely general parametric model. If you want a height of 10, and you need also a depth of whatever 8, then instead of starting a new project and clicking around and so on, well then you just go like that. So that needs some more depth. Oh, of course, it's again, there's the wall that sort of is the weak link here. So let's try to say 1500. Yeah. And then you can do with a slightly, well, it sort of depends whether it's still the wall that breaks. Okay. But that's the idea. Suppose you had a very strong wall. Suppose you had a rigid wall. We could try to well, we can actually modify the script to quite easily to apply a rigid wall. We can also see how what it's called. It's called rigid plate here in the UI, and how does it work in Python? Material project get material is called. You can, instead of getting the general plate, you have to get the rigid plate. So it's one line that needs to be modified here. It's this one. Let's comment that out, and let's have a new material, rigid plate. And then let's try to close that. Oh, okay. So the rigid plate doesn't have a property NP, of course. That kind of belongs up here. Yeah. So 1.57 approximately. And then suppose that you had a target factor of safety of 1. and you would iteratively adjust the depth of the wall to get to 1. Try with 8 meters. That was still more than enough. Say 5, that is probably too little. That was probably 5.8. So that was a little bit too much. I think you get the idea that you adjust the depth of the wall iteratively to get to your target factor of safety. And actually, if I go back to the presentation, that is the second exercise. I would like to consider implement the procedures to determine the necessary D. So the necessary depth given a target factor of safety, which may be 1 or 1.2 or whatever. In order to do that, I have a suggestion for a sort of a very simple bisection algorithm that we actually use a lot internally in GX, and that's also quite useful here. It's a very simple algorithm. So suppose we have an equation we want to solve, which looks like this. We have say a function FOS, factor of safety. The factor of safety is a function of the depth, and we want to solve this equation. We want to get to a factor of safety equal to a specified target factor of safety. So if you look at it, situation down here, we have the FOS versus D. It may be a function that sort of looks like this. Definitely it increases with increasing D. And then we have our target, and we have a D star here corresponding to the target, and it's this D star that we are seeking. And so the bisection algorithm, the way it works is that you, of course, need to specify your FOS target. Then we have a minimum D and a maximum D. I've said 0.1 and 10 here, but it can really be anything. And then we have an initial D. I've said 5 here. And then the way it works is that you go through iterative loop where you determine the factor of safety for the given D. In this case, in the first time you run through the loop, it's going to be 5. You get the factor of safety. You have your minimum and maximum D. Here, you determine the factor of safety. And if the factor of safety is greater than the target factor of safety, like here, well, then you adjust the upper limit down. Then you know this D max of 10 is definitely enough. So you can adjust it down to the D that you have just used to determine a factor of safety greater than the target factor of safety. So like that. And then you set your new D equal to the average between the new maximum and minimum Ds. So that's somewhere here. And you are then below the target factor of safety. And you would then adjust the minimum D. You know it needs to be at least here. And then again, you take the average, you try again, get the factor of safety, it's above, adjust the upper limit down, go again with the average, and it's below the lower limit, and sooner or later you're going to narrow this range in until it's enough. And I have said, I have a convergence criterion here saying that if basically if the factor of safety is sufficiently close to the target factor of safety, the tolerance is 0.01, then break off the iterations. So you can use anything, of course, but I think this one is not too bad. So let's try to do that with let's try some other dimensions, more realistic dimensions, a height of 5, and we can start with an initial depth of 5 as well. Then we have to be a little bit careful. So this H here is fixed, but this one here is the one we want to be modifying. So let's just take that out here and put here. And so we had also the FOS target, the mean D max. Target, let's say it's 1. The minimum is, I don't think there's any reason that it can't be 0. And max, we can say 10. We need to select some number. It can again be anything, but the more reasonable it is, the faster this whole thing will converge. So that to be all that reasonable though, but let's say 0 and 10. That's with a height of 5, then it's probably not going to be above 10. And then we want to enclose everything we have basically in a loop. I say like this loop here, right? What we have here is basically, it's this line here. We calculate the factor of safety. So for eta in range, let's have another one called max eta. Oh. Let's just try with a single iteration to see if it works. Do what we have just done. Just indent this. Basically calculate the factor of safety. We can print it as well. I want to print D and then factor of safety. And then we come to this second part here. So if D is, no, if FOS is greater than FOS target, then D max is equal to D, else D minimum is equal to B. And then we have the new D is the D min plus D max divided by 2. And then if FOS minus FOS target is less than 0.01, then break it off. Let's see if this works for a single iteration. That does not look unreasonable. Always want to just, check that everything looks more or less reasonable. So this looks pretty good. And then let's go to something like 20 iterations, which should be more than enough. And then as you can see, it is, it calculates and sets up a new problem with a new D every time you run through the loop, and you can see it here. So the first one was 5 meters, then 2.5, that was not enough. So then it's going to be somewhere in between those. It's going to be exactly in between those two. We try 3.75, that's too much. So then it's going to be in between, yeah, like that. And then we're getting closer now. .9922, okay. We could have had an extra condition here that it shouldn't terminate unless the FOS is actually also above the factor of safety, the target factor of safety. But this is how it works. So this, of course, once you have the script, and I hope I sort of have convinced you that setting up a script is not a huge amount of work. Once you have that script, then everything else becomes a lot easier. What you would otherwise do manually, adjust this one up and down and rerun, just becomes completely automated. And so that's really the strength of Python scripting. Just to finish off, we We have in GX, as you'll probably notice, we have these icons up here. We actually opened the Spider IDE by this icon here. And these icons are what we call them plugins. They open, they open up what we call plugins, and one of the plugins is called Spooks, and there's actually both an anchored and a cantilever version of that. So that's exactly kind of what we have done. We have a retaining wall um, with some capacity, with a roughness, with some surcharge, and we can then, there's various options. You can calculate the factor of safety as we've just done. Um, so this is nothing more than a script of the kind that we've just developed. And then there is a simple user interface wrapped around it. And this simple user interface allows you for inputting data easily and taking the results. In this case, the sectional forces are shown, and earth pressures are shown as well. The collapse mechanism is the results are taken out of GX and imported into this small app here, and the actual numbers, the data, the depth coordinate, and then the sectional forces and the earth pressures and water pressures, if there are any such, are available here. That it's a more advanced version of what we've done. You can have multiple soil layers as well. So 15, 0, let's say 35, 18. So then you have a model with two layers, and you can have anchors. You can have also as many anchors as you like. This is what we call a plugin, and it is nothing more than the kind of script that we have developed, plus then a simple UI. And this simple UI is also written in Python. All the code that produces this is available. There's nothing hidden. If you right-click on and open the plugin folder, well, you'll see the code here. And the main file is this one here, where all the code is available and can be modified as well if you like. I will have a video soon about basically creating these plugins. But for now, I think this is it. So thank you. Bye.